A database's performance, it pretty much lives or dies by one single component. We're talking about the buffer pool manager. It's kind of the unsung hero, right? The crucial bridge between that lightning-fast memory and, well, brutally slow disk. If you get this right, your database just flies. But if you get it wrong, you end up with a system that's technically correct, sure, but also completely unusable. All right, so here's the plan. We're going to dive right in and build a buffer pool manager from the ground up, starting with the big, ugly problem it's designed to just obliterate. We'll look at the tyranny of disk, cook up a simple cache, make it concurrency safe, and then figure out how to survive nasty sequential scans. After that, we'll tackle dirty pages and durability, and finally, look at some pro-level optimizations.
Okay, first things first. To really get why a buffer pool even exists, you've got to appreciate just how insanely slow disk I/O is. And I'm not just talking kinda slow. It operates on a completely different timescale from everything else in your computer.
And when I say different timescale, I mean, look at this number. We're talking over 1,000,000 times faster. Accessing data in RAM versus fetching it from a spinning disk isn't even a fair fight. Think about it this way. In the time it takes for a single disk to find your data, a modern CPU could have executed billions of instructions. Forcing your CPU to wait on the disk is like telling a Formula One driver they have to stay behind someone walking. It's just painful. And here's why it's so slow. Reading a page from a disk isn't just one thing. It's this whole mechanical dance, right? The physical head has to move to the right track. That's seek time. Then the platter has to spin around to the right spot. That's rotational latency. Then you can finally transfer the data. All these little physical movements add up to milliseconds. And trust me, milliseconds are an absolute eternity in CPU time. A simple query that needs, say, 4 page reads, that could easily take over 30 milliseconds. Kiss your performance goodbye. So what's the solution? Well, we build a component whose entire job is to wage war on this latency. Enter the buffer pool manager. It carves out a huge chunk of RAM for itself and says, this is my cache. And from this point forward, it's the exclusive gatekeeper. No other part of the database is allowed to talk to the disk directly. Everything, and I mean everything, has to go through the BPM. All right, so let's do it. Let's design the simplest possible version of this cache. We're going to strip it down to the bare essentials and just see how the whole thing works.
Okay, so at its core, the BPM is really just juggling 3 key things. First, you have the frames. This is the actual memory, the raw space. Think of it like an array of parking spots, each one perfectly sized for one page of data. Then you've got the page table. This is your parking lot directory. It's a hash map that tells you instantly, hey, page 123? Yeah, it's in parking spot 7. And finally, the free list, which is, well, it's just a list of all the empty parking spots. Super simple.
So when a request for a page comes in, the logic is pretty straightforward. Step 1, check the page table. Is this page already in one of my frames? If the answer is yes, that's a cache hit. Awesome. We just give back a pointer to that memory and we're done. But if it's not there, that's a cache miss. So we find an empty frame from our free list. We do that slow, painful read from disk to load the page into the frame. We update our page table to remember where we put it, and then we return the pointer. It sounds simple, it sounds effective, and it is completely, utterly broken the second you introduce more than one thread.
And this is where things get real. Because in the real world, you have multiple threads hitting the database all at once. And our simple little model, it just completely falls apart. This forces us to create a non-negotiable contract, a safety rule to prevent the absolute worst-case scenario. Silent, catastrophic data corruption.
So let me ask you this. What happens when one thread, let's call it thread A, is happily reading a page that's sitting in a frame, and at the exact same time, thread B comes along and tells the buffer pool manager, hey, I need a frame, and I'm going to evict the one thread A is using? This question right here, this is the heart of the single biggest danger in this whole design.
Let's walk through this nightmare scenario, step by step. Okay, so thread A requests page 5. The BPM does its job, loads it into, say, frame 7, and hands thread A a memory pointer. Everything's fine. Thread A starts reading or maybe even modifying the data in that frame.
But then, along comes thread B. It requests a page that's not in the cache. The BPM looks around for a frame to use, and it picks, you guessed it, frame 7. It evicts page 5 and overwrites that exact same piece of memory with brand new data for, let's say, page 99.
And here is the absolute disaster. Thread A has no idea this happened.
Its pointer is still perfectly valid. It still points to the memory address of frame 7. But the data at that address has been completely swapped out from under it. So thread A is now reading and, even worse, writing to the data of page 99, all while thinking it's working with page 5. This is silent data corruption. It's the kind of bug that destroys databases and careers. So how do we fix this? We introduce a beautifully simple idea called the pin/unpin contract. It's really just basic reference counting. When a thread fetches a page, it has to pin it, which just means we increment a little counter for that page. And when the thread is finished with it, it must unpin it, which decrements the counter.
And this leads us to the one absolute unbreakable capital R rule of buffer pool management. A page with a pin count greater than 0 cannot be evicted. Ever. Period. That page is considered pinned and is totally off limits to our eviction logic. This one simple rule completely prevents that nightmare scenario and gives us our memory safety guarantee.
Okay, awesome. Our cache is now safe from concurrent access disasters. But that brings us to the next big problem. We don't have infinite memory. So when the time comes and we do need to kick a page out to make room, how do we decide which one? How do we intelligently pick our victim from all the unpinned pages?
Now, the first thing that probably comes to mind is LRU, right? Least recently used. Just evict the page we haven't touched in the longest time. Makes sense. Except, for databases, it's actually a terrible idea. And the reason is something called buffer pool pollution. Imagine a huge query, like a select count star on a massive table. That query is going to march through the buffer pool, reading thousands of pages, each one used exactly once. And in the process, it's going to kick out all of your actually valuable, frequently used pages, like index root nodes and important metadata. Your cache gets filled with useless, one-time use pages, and performance just falls off a cliff. So what we really need is a scan-resistant eviction policy. This brings us to a showdown between the naive LRU and a much, much smarter algorithm called clock, which is sometimes called second chance. And the key difference is right there in the name. Where LRU is totally vulnerable to these big scans, clock is specifically designed to resist them.
The way the clock algorithm works is it's so clever. Imagine all our frames are arranged in a big circle, like a clock face, and there's a clock hand pointing to one of them. When we need to find a page to evict, the hand starts sweeping. First, it looks at a frame. Is the page pinned? If yes, can't touch it. Skip. Move on. Okay, so it's not pinned. Next, it checks a special reference bit. Has this page been used recently? If that bit is a 1, it means yes, so the algorithm gives it a second chance. It flips the bit to 0 and moves the clock hand to the next frame. The very first frame it finds that is both unpinned and has a reference bit of 0, that's our victim. That's the one that gets evicted. It's this simple second chance mechanism that so elegantly protects our important, frequently used pages from getting kicked out by some big, dumb scan.
All right, so our cache is safe and it's smart about eviction. We're getting there. But we've only talked about reading data. What happens when a thread actually changes a page in memory? We need a rock-solid way to track these modifications and make sure they get back to disk safely without losing data.
For this, we use what's called a write-back caching policy. It's actually pretty simple. When a page gets modified in memory, we don't immediately write it back to disk. That would be slow. Instead, we just flip a switch on it, a little isDirty flag, to remind ourselves that it has unsaved changes. We only actually write that dirty page to disk when we absolutely have to, like right before we're about to evict it. This is a massive performance win, because you might modify that same page 10 times in memory, but it only results in one single efficient write to disk later on. But, and this is a huge but, to make sure we don't lose data, if the server crashes, the BPM has to follow another golden rule. This one is called write-ahead logging, or WAL. And the rule is this: the log record describing a change must be written to durable storage before the dirty page itself is. This strict ordering, log first, then data, is the magic that allows a database to recover perfectly even after a sudden power failure.
Okay, so we've covered the fundamentals: safety, smart eviction, and durability. Now let's talk about how these core ideas evolve into the kinds of advanced features you'd see in a real production-grade database system. Because the basics are crucial, but the real world, well, it always demands more.
Yeah, a production-grade BPM is a whole different beast. It isn't just reactive, it's proactive. It uses prefetching to look at your access patterns and intelligently load pages into memory before you even ask for them. It's also cooperative with buffer pool aware algorithms where things like the query planner actually talk to the BPM to coordinate big memory allocations for sorts or joins. And of course, it is tested relentlessly with things like a concurrency gauntlet to prove its safety under fire. Many systems even use multiple buffer pools, specialized pools for, say, index data versus user data, so a big scan on one doesn't wreck the cache for the other.
And all of this really leaves us with one final, crucial question to think about. Your cache hit rate might be 99%, and that feels great, right? But is your data actually safe when the power suddenly fails? It's so easy to get obsessed with just the performance numbers, but a sky-high hit rate means absolutely nothing if you can't also guarantee that your data is safe, consistent, and durable. And that, right there, is the entire point of a well-designed buffer pool manager, giving you the incredible speed of memory, but with the rock-solid safety of disk.